This is Kung Fu Review video number 4. We're going to be going over all the key things you need to know about gases. So have your notes ready and film out as we go. First thing is gases are, the whole idea behind gases is the kinetic molecular theory, which basically talks about that all molecules are in motion. There's key things about gases. We know gases are basically large number of particles, constant random motion. They move in a straight line until they collide with the walls of their container or another particle. The particles, most of a gas is basically empty space, and there's no force of attraction between gas particles or the particles of the container, and then the gas collisions are perfectly elastic. Those are all key parts. One of the other things that comes up is, and they're emphasizing this year, is the average kinetic energy is a collection of gas particles. What that means is kinetic energy and temperature is the exact same thing for a gas. One of the key things from a theory point of view they want you to know is when you have it, like for example, oxygen at 25 degrees Celsius, if you notice right here, the molecular speed, what it is it's the average movement of all the molecules in a gas represents temperature. Some are higher, some are lower. Same thing if you look at the speed of oxygen molecules at 1,000 degrees Celsius. They're not all moving the same speed. There's some high, there's some low, but it basically depends on the average. It really is what it is the temperature is the average of all the high and low speeds all together, and as you increase temperature, the distribution of speeds will always be across a wider range. So if you notice here, this is at 25 degrees Celsius, basically, that's what that's saying. At 1,000 degrees Celsius, you would have a wider range of gas molecules. All of the baby gas laws, or the simple gas laws, are based off the combined gas law, which is when you're focusing on only 3 variables, P, V, and T. So to get any of the, if you're given 5 values, which they rarely give you on the AP exam, to solve the problem, you would just basically plug into the combined gas law. But what they usually do is they'll give you a version of one of the baby or gas laws by holding one of these constants. For example, if I held temperature constant, I get Boyle's law. If I hold pressure constant, I get Charles' law. If I hold volume constant, I get Gay-Lussac's law. That's basically where it comes from. So a key thing to remember when you're taking your test is P1 V1 over T1, P2 V2 over T2. It's easy, and you can just kind of plug it in. So when we talk about Boyle's law, we talk about it from a graphic standpoint, P and V. It is an inverse relationship. It's the only gas law that is inverse. That's key that you need to know. So it's an inverse relationship. Pressure and volume are inversely related, so we end up with P1 V1 is equal to P2 V2. Charles' law is a direct relationship of volume and temperature. You're going to end up with V1 over T1, V2 over T2. Finally, Gay-Lussac's law, same thing, as a direct relationship. Pressure and temperature of a gas are directly related, so it's P1 over T1 is equal to P2 over T2. And again, all those values, pretty simple calculations. If they give them to you, you just plug it in. If it's on the free response section, you have a calculator. If not, you'd have to deal within the multiple choice. Then we get to ideal gas law. You use the ideal gas law to find the volume or pressure of a gas, especially if it's not at STP. This is what you're pretty much going to use. You can't assume a gas is at STP on the AP exam unless they actually list it. So if you look here, this is pressure. It has to be in atmospheres. Volume has to be in liters. R is the constant right here, which is liters, atmospheres, moles, and Kelvin. And this is the constant they give you on the AP exam. So you have to be aware of your pressure, volume, and temperature always has to be in Kelvin anyway, units, to make sure that it cancels. So you have Pivner in here. There's 2 derivations of Pivner. This is the ideal gas law that will usually have you solve for volume or pressure. So you just algebraically rearrange. But the density of a gas, remember, pandas, mall men, riding tricycles is not provided for you in that format, so that's something you'd have to memorize. The other thing is when you're calculating the molar mass of a gas, molar mass, Mickey Mouse is a great vice president, is what they teach you in honors. Again, another derivation. G in this case is going to be grams. All the other values you know. MM in this case is molar mass. Dalton's law of partial pressure appears a lot on the exam, especially in the multiple choice. Remember, it just states that the total pressure of a mixture of gases is just summing the values up. So if they want total pressure, they would give you several gases, you would add them together. But usually what happens is they provide you a total pressure and they want to know the partial pressure of a gas. That's where mole fraction comes in. Mole fraction is part of moles over total moles. So you basically, if you have to find mole fraction of something, find moles of all the gases in whatever part of the gas that you want. Let's say gas X. You put the part of the mole actually is equal to the weird X mole fraction. Once you find mole fraction, you can just always multiply times the total pressure to get, because that's where Raoult's law comes in. So ultimately, let me erase this here. You come and think of it like this. Part moles, I should have wrote it like this. Part moles goes on top, total moles goes on the bottom. And then when you do your calculation, you get a mole fraction, which is going to be a decimal. So you get your weird little X thing, and then you always multiply that times the total pressure to find the partial pressure of a gas. This is pretty much on the multiple choice every year. The other derivation of that is what we call whenever you collect gas over water, because in chemistry we generate gas and we collect it over water. So here's an example, if you notice here, of hydrogen and water vapor in a container. We collect it over water so we can measure the volume of the gas by displacement, but we also get water vapor in there as well. So if we want the pressure of just the H2 gas, what do we have to do? When you go to find a dry gas, it's called the dry gas problem. All you have to remember is take the pressure of water, the vapor pressure, which should be given you in the problem in the AP exam. You basically subtract the vapor pressure of water, you move it over there. When you subtract the vapor pressure of water, you're going to find the dry gas means without the water. So if you subtract it from the total, you're left with the pressure of the dry gas. All right, deviations from ideal behavior. Remember the ideal gas law, we have some assumptions. Real gases, well, ideal behavior is as long as pressures are low. So if we have low pressures and temperatures are relatively high, then the gases are far apart and they exhibit ideal behavior. When they get close together, and the two conditions that cause them to get close together are high pressure is one you need to write down. High pressure will put the gas molecules closer to each other, and low temperature. Either one of these conditions or both of these conditions is going to cause the gases to get close to each other and exhibit non-ideal behavior. The other thing they test for on the exam a lot is if they're not mentioning pressure or temperature, the only other deviation from ideal behavior is the gas that has the most intermolecular forces. So if you're comparing two gases and one of them is polar versus the other molecule being nonpolar, the most IMF that you have, that's where you apply the IMF rules that you learn. The greater the IMF in a gas, the more deviation from ideal behavior. All right, last thing is gas theory. They ask this all the time, especially on the multiple choice. So first and foremost, they'll ask you about molecules of gas. Which gas has the most molecules? Key thing that they do a lot of is remember this. If you have the same P, V, and T, your N must be the same, which means you have the same number of gases. So check. If you have the same P, T, and V, and this is a question they use a lot, it means N, same number of molecules, basically. Speed of a gas. Speed of a gas is directly related to its molar mass. The smallest molar mass of a gas, so the smallest molar mass equals the fastest gas. So that's the fastest gas. So if they ask you to compare gas molecules, it's based on molar mass. Lighter the molar mass or smaller, the faster it'll be. Average kinetic energy is the exact same thing as temperature. They use this as a trick question all the time. So if you have gases that are at the same temperature, you want to look for this. Same temperature means same kinetic energy, because temperature is a measure of kinetic energy. Do not fall for that one. Next one that comes up, they'll ask you which one has the greatest mass of a gas. When they ask you who has the greatest mass of a gas and they're given the same quantities, it's going to be whoever has the greatest molar mass. So you're looking for the largest molar mass if you're comparing the same amounts of gases. Will be the greatest mass because the moles will be the same, so you just multiply times molar mass. Density of a gas. If you think about density of a gas, remember density is equal to pandas, mall, men, riding tricycles. Well, if you're comparing two gases and they're at the same pressure and temperature, means pressure is a constant, temperature is a constant, and R is a constant. So there's a direct relationship between the molar mass of a gas. The higher the molar mass of a gas, the more dense it's going to be. The more dense that gas will be. So that's the key thing. Compare the molar mass of the gases. The largest molar mass of a gas will have the greatest density. Rate of effusion. Remember, effusion is escaping out of a pinhole-sized container gases. That relationship is the smaller the molar mass. So the smaller the molar mass equals the faster rate of effusion. Faster effusion. And those are key. These come up every year on the AP exam, the gas theory ones. So rate of effusion, smaller the molar mass, faster the effusion rate. Density is related to molar mass directly. Greatest mass of a gas is related to molar mass directly. Average kinetic energy, check the temperatures. If they're the same temperature, same kinetic energy. Speed of a gas molecule, smallest molar mass means it's going to be the fastest gas. The number of gases, check P, V, and T before you even start. All right, this is a review of gases. Now you want to make sure you go and do the Kung Fu quiz and submit your answers. Have a nice evening.